All right, students, we are ready to start a new unit here. This unit is about chemical reactions. We have spent considerable time studying the properties of matter, both elements and compounds. Now it's time to see these substances in action. Here are some of the topics we're going to be covering in this unit here. We're going to divide it into several sections to make your studying a little easier to focus. So this first section, we're going to talk about chemical equations. So a chemical change, as we've seen before, is one in which the identity, the composition of substances changes. Now, a chemical change may consist of a single or multiple processes. A process in which one or more substances is changed into one or more new substances, we call it a chemical reaction. And as you can understand, a chemical change may consist of a single chemical reaction, or it may consist of multiple chemical reactions. For example, we could say that the process of digesting a meal is a chemical change, but it consists of many chemical reactions. The way we represent a chemical reaction is by using a chemical equation. Chemical equation uses chemical symbols to show what happens during a chemical reaction. So let's look at a sample chemical equation here. Of course, you notice the presence of that big arrow in between that we use to indicate that there's a process, that whatever is on the left is being changed into whatever is on the right. In a chemical equation, the substances on the left of that arrow are called reactants, and the substances on the right of the arrow are called products. You'll notice that there are some numbers in front of some of them, some of the formulas, and we call those coefficients. Notice that for the oxygen here, the O2, there is no number written, but we are implying that there is a coefficient there. It's just that it's 1, and we don't write the 1. Now, just like in language, how would you read a chemical equation? Let's look at this one here. How would we read this? Well, there's several ways we could read it, just like any equation, just from left to right. 2 atoms of magnesium and 1 molecule of oxygen makes 2 formula units of MgO, or magnesium oxide. Now you remember that if you have an equation, x equals y, if you multiply both sides by the same number, you get another equation. It's still an equality. So let's say we multiply all of these times Avogadro's number. So 2 times Avogadro's number atoms of magnesium plus 1 times Avogadro's number of molecules of O2 make 2 times Avogadro's number of formula units of magnesium oxide. But remember, an Avogadro's number of items is, that's right, a mole. So we could read the equation in moles. So 2 moles of magnesium and 1 mole of O2 makes 2 moles of MgO. If we wanted to convert those to grams, we could simply multiply times the molar mass of each one of these substances and say that 48.6 grams of magnesium and 32.0 grams of O2 makes 80.6 grams of MgO. Notice that in this case, we simply took the moles and we multiplied times a conversion factor, which is the grams per mole of each substance. What you cannot do is you cannot read the chemical equation as if the coefficients represented units of mass. So 2 grams of magnesium plus 1 gram of O2 makes 2 grams of MgO. That is incorrect. We have to read the equation in either atoms and molecules or moles. Or if we use grams, we have to account for converting the moles into the proper numbers of grams. Now, the substances involved in the chemical reaction may be solid, liquid, gases, or they may be part of a mixture. In order to indicate this information is added to the equation by placing the appropriate symbols after the formulas. So for solid, we use S. For For liquid, we use L. For gas, we use G. And for an aqueous solution, in other words, a mixture in water, we use AQ. Notice that these substances are indicated inside parentheses, and they are not subscripts or superscripts. They should be written in the same font as the rest of the equation. The next step in writing a chemical equation is we have to balance it. So in a balanced chemical equation, the same number of each atom appears on each side. Why? Conservation of mass. During a chemical change, the total mass is conserved. The atoms are the same. They are just rearranged in a different form. So let's look at the steps for balancing a chemical equation. First, we're going to write an unbalanced, also called skeletal equation, using the correct formulas for all reactants and products. The idea here is to make sure that we have the correct formulas and that we have the correct substances on the reactants side and the correct substances on the products side. Step number 2, once we have the formulas, we can't change them, so we're going to add appropriate coefficients to balance the numbers of atoms of each element. And we'll show you how to do that in a moment. Step 3, check the equation to make sure the numbers and kinds of atoms on both sides of the equation are the same. And then, if for some reason you find that your coefficients are not in their simplest ratios, step number 4 would be to simplify the coefficients. Okay, so with this in mind, let's go ahead and do a couple of practice exercises here. Let's balance these two reactions here. We're going to write the equations and then balance them. Methane gas combines with oxygen to produce carbon dioxide and water vapor. And the second one, when potassium chlorate is heated, it decomposes to form solid potassium chloride and oxygen gas. Let's go to our paper board and then we'll come back to our PowerPoint. Let's get started by making sure that we have the correct formulas. Remember, we start with an unbalanced equation. All we're trying to do is make sure we have the correct formulas. They didn't tell us what methane is, so we're going to have to look it up. And it turns out methane is CH4. Then it says combines with oxygen. Remember what we discussed in the previous unit. Whenever they say oxygen with no other information, we have to assume that it means the naturally occurring form of the element, which is O2. And then it says that the products are carbon dioxide and water vapor. I think we talked about this when we discussed combustion analysis in the previous unit. We said that the burning of substances that have carbon and hydrogen in them results in the production of carbon dioxide and water. So let's start out by writing the unbalanced equation first. So let's say CH4 combines with O2, so let's put O2 there, and it produces carbon dioxide and water vapor, and those are our actors on the stage here. Notice that this is completely unbalanced. We are not trying to have a straight up balanced equation right away. There's several ways you can go about this. I'm going to show you first the long way. And the reason I show it to you is because sometimes it helps. All right, so let's first put a little wall here and say these are the reactants, these are the products. Let's see what we have here. We have carbon, we have hydrogen, and we have oxygen, correct? How many atoms of each do we have? Well, we have 1 atom of carbon, we have 4 of hydrogen, and we have 2 atoms of oxygen. So what we're doing here is we are just counting atoms. On the right side, we should have the same types of atoms, otherwise the reaction is not obeying the law of conservation of mass. So we have again C, we have H, and we have O. And let's see, on this side we have 1 carbon, we have 2 hydrogens, And we have, careful, 2 plus 1, 3 oxygens. So the goal now is I need to make sure, in order to obey the law of conservation of mass, that not only do I have the same kinds of atoms on both sides, but the same numbers of atoms. Remember, in a chemical reaction, all that changes is the way the atoms are arranged, or let's say connected to each other. So how can I change this equation so that I can balance the numbers of atoms without changing the formulas of the reactants and products? Well, the only way I do that is by changing the coefficients. At this point, we have the carbons are balanced. So I probably don't want to touch the CH4 and the CO2. So let's try then the other two atoms we have here. We have oxygens and we have hydrogens. The oxygen, though, is present in 2 of the products. So it'd be hard to balance that. However, the hydrogen is only present in 1. So without changing the formula of water, what we do is we change the coefficient that's in there. So let's rewrite this equation again. I'm going to do CH4 plus O2, CO2. And what I'm going to do is I'm going to put a different coefficient here. Right now, each one of these has a coefficient of 1. So how do I get 2 to become 4 without changing this formula into H4O, which would be incorrect? That's right. Let's put a coefficient of 2 in there. And now we'll put the rest of the formula. And let's see what was the result of that. Again, on this side, I have still 1 atom of carbon, 4 of hydrogen, and 2 of oxygen. I didn't change anything on the left side. On the right side, I still have 1 atom of carbon, but now I have 2 times 2, I have 4 atoms of hydrogen. In other words, now at this point, my hydrogens have become balanced. I have the same number of atoms on both sides. However, that coefficient now also affects the oxygen, which means that now I have 2 plus 2, I now have 4 atoms of oxygen. So now I had to balance it. But fortunately for us, and the way it usually happens, is that now on the left side, the oxygen is isolated into a molecular form, just oxygens in it. So what if I simply put a 2 here, and let's see what that does for us. Let's rewrite the equation. CH4 plus 2O2, right? And we have CO2 plus 2H2O. Notice that what I did was I changed this coefficient over here. Let's do another recount of atoms. I now have on the left side still 1 carbon, still 4 hydrogens, and now I have 4, 2 times 2, oxygens. On the left side, in this second step, I didn't change anything, so I still have 1 carbon, 4 hydrogens, and 4 oxygens. So as you can see, we have balanced the coefficients. We have balanced the atoms on both sides of the equation. Now, in order to write down a properly balanced equation, we have to now put in the physical states. So they told us that methane was a gas. So CH4G. We have 2 molecules of oxygen, but we know that oxygen exists in the form of a gas also. Okay, carbon dioxide. What do you guys think that is? I mean, they don't tell us, but we know that carbon dioxide is the gas that we exhale when we breathe, right? So we know it's a gas. Now the water could be liquid, could be gas, but it tells us here that it's water vapor. So that means that this time the water product was in the gas state. And we now have a fully balanced equation. And this is actually the equation for something we're going to learn is called the combustion of methane. This is the chemical reaction that happens in your Bunsen burner in the lab when you light it. Okay, let's tackle now the second reaction here. When potassium chlorate is heated, it decomposes to form solid potassium chloride and oxygen gas. So like before, let's start out by making sure we have the formulas. So I think we all know what potassium chloride is, right? KCl. Oxygen gas, again, don't forget, in the absence of any other information, we default to the natural form of oxygen, O2. And then potassium chlorate, we'll probably have to look that up because I have not made you memorize these things. So we can see that chlorate would be the anion here, but it must be one of those polyatomic ions. Let's look it up and let's find out that what we have here is KClO3. And it says that it gets heated and it decomposes, which means it breaks down to form potassium chloride and oxygen gas. Again, this is my unbalanced equation. This is my starting point. In the previous example, I showed you kind of like a long way, a step-by-step way of doing it. So let me show you a different way. It's kind of like more of a shortcut. Once more, we're going to write down what are the elements on each side. And once more, they should be the same elements on both sides because of conservation of mass. Our task now is to find out how do we make them be not only the same kinds of elements, but the same numbers of atoms. Okay, on the left side, we have 1 potassium, we have 1 chlorine, and we have 3 oxygen atoms. At this point on the right side, we also have 1 potassium and 1 chlorine, but we only have 2 oxygens. So the goal now is, how do we equalize this so that we have the same numbers? Well, here is my strategy. I can equalize the oxygens first, knowing that any change in the coefficients I make on the reactant side is also going to affect K and Cl. But because those are present by themselves as a compound on the product side, and they're still in a 1-to-1 ratio, I should be able to get that done. So how do I equalize the numbers of oxygens? In this case, since one is even, the other is odd, we probably are safer looking for a common multiple, which would be 6. So what I'm going to do is I'm going to put a 2 here, and I'm going to put a 3 over here. As a result of that, I'm going to end up on the right side having 3 times 2, which is 6. I'm going to do a forward slash, and I'm going to put the new number in there, which is 6. On the left side, again, I had 2 times 3, so that is going to generate 6. I'm going to use a forward slash and put a 6 in there. However, and this was our first step that we did here. Let me write this as our first step. As a consequence of the change in coefficient on the left side, I generated a change in the potassiums and the chlorines. So what I'm going to do for that is I am going to put in a downward slash or reverse slash here, and I'm going to put the new numbers that were generated by that change. So this is how I follow things. Now I'm using colors here just to kind of highlight it. You don't have to do it by colors. But essentially the forward slash gives me the change that is directly caused by the change in coefficients. And The reverse slash, or the downward slash, gives me the change that came up as a consequence of that change of coefficients. So what do I do now to change it on the other side? Well, notice that they're still in a 1-to-1 ratio. They are in a 1-to-1 ratio here. So what I can do now is I can put a coefficient of 2 here. This will be my second step. And as a consequence of that second step, I can now do forward here and put in 2 potassiums and 2 chlorines. And now I have my equation balanced. Of course, if I want to make everything right, I want to put in physical states. So I have 2KClO3. And we wonder, well, what would be the physical state of that? It is an ionic compound. And what did we say about ionic compounds? Correct. Under normal circumstances, they are going to be a solid. More specifically, a crystal lattice of alternating ions. And then we're going to put our forward arrow, and then we have 2KCl. They already told us that it was solid, and they did a favor in telling us that the oxygen was a gas, but we knew that, right? So 3O2 in the gas form, and that would be our final balanced equation. Now, sometimes chemists like to indicate any specific situational conditions, in other words, circumstances. And in this case, it says that it was heated. So many times what we do is we write the word heat here. In the old days, scientists used to put like a little triangle there to represent like a flame. But since we don't always use Bunsen burners to do this, sometimes we can use hot plates or other sources of heat. We just write the word heat. And that is the balanced equation for the decomposition of potassium chlorate. Decomposition of KClO3. This is a reaction that we're going to use later in the semester when we study the properties of gases. Okay, after that practice, let's go ahead and review some things. For example, let's avoid common errors that may happen when we balance chemical equations. One common error: do not change the formula of a reactant or product. That is the objective of the first step. Let's say that I have this unbalanced equation here. Notice that the nitrogens are okay, there's 2 on each side, but there's only 1 oxygen on the right side. I cannot arbitrarily decide that I'm going to change the formula of the product just to make the atoms of oxygen balance out. Okay, you cannot do that. Once you've established the formulas, the only thing you change are the coefficients. Another error is you cannot add new reactants or products. So in the above case, you might be tempted to say, well, why don't we just put an extra atom of oxygen there on the product side, and that way we have 2 oxygens just like on the left side. You cannot put in reactants and products that are not part of the reaction. Number 3, sometimes as we go through the motions of balancing the equation, we might have carried out too many steps, and we cannot leave multiples of the coefficients when writing the balanced equation. In other words, you want to bring the equation down to the simplest ratios of coefficients. So let's say that we're trying to balance this equation and ended up with what's in here. As you can see, the coefficients 4, 2, and 4 are multiples of 2. So you could simplify this to 2N2 plus O2 and producing 2N2O. So make sure you don't make that mistake, okay? Now, we're going to tackle now some special situations by doing the following practice exercise. Let's balance this equation. Butane reacts with oxygen gas to form carbon dioxide and water. Let's go to our paper board for this. Let's go ahead and balance this equation. This is also a combustion reaction, but this is for butane, which is actually the component of lighter fluid. So let's go ahead and write down the unbalanced equation first. C4H10 reacts with oxygen gas, and we've already determined that that should be O2. And then we're going to get carbon dioxide and H2O. Oh, let me slide this over here a little bit so we can see the whole thing. There we go. Sorry about that. Okay, let's use the shortcut method here. And let's start out by listing the elements on both sides, CH and O. CH and O. Let's see how many we have on each side. We have 4 atoms of carbon. On the left side, we have 10 atoms of hydrogen, and we have 2 atoms of oxygen. On the right side, we have 1 carbon atom, 2 hydrogens, and 2 plus 1, 3 oxygens. The first thing we try to do is let's balance something that is present in only one compound on each side. So I don't want to start with oxygens because on the right side they're present on 2 compounds, and that might make it kind of not impossible but a little harder. So I think you agree that the one that stands out as the easiest target first would be the carbon, right? Because all I need to do is I need to have 4 carbons on the right, and there's only one compound that has carbon in it, and that would be the CO2. So as a result of that first step here, I'm going to end up getting now 4 carbons here. But as a result of that, I'm also changing the oxygens. So now I have 4 times 2, 8, plus 1 is 9. So I'm going to put a downward slash here and change this to 9. And this is also as a consequence of step number 1. Okay, let's tackle now the hydrogens. As we can see here, we have 10 on the left side, 2 on the right side, but they are all in the water molecule. So to get this to be 10, I can add a coefficient of 5 here. This will be step number 2. And as a result, now I have 10 units of hydrogen, atoms of hydrogen, I'm sorry. But as a result of that also, I now have 8 and 5, 13 atoms of oxygen here on the right side. Well, in the previous example with the combustion of methane, it was easy because this was an even number and it was simple to find a multiplier to get me a pair of oxygens to go to that number. We can't do that right now. So there's several ways we can go here. But here's what I want to tell you. Remember, when we quote-unquote read a chemical equation, the coefficients can be interpreted as, let's say, molecules of compound, but they can also be interpreted as moles of compound, or in this case, element. So in other words, I could say that on this side, what I have right now is I have 2 moles of oxygen, but I need 13. So how about if I do something very provisional here, and it is I'm going to try to generate this so that it becomes 13. Notice that this change is not going to affect the other compound on the reactants side. How do I get this to become 13? Well, since these are moles, I'm going to simply multiply times 13 over 2. Now you might say, wait, but it's supposed to be a whole number. Well, we're not done yet. This is just an intermediate step. Notice that 13 halves times 2 gives me 13. I can do that because I'm thinking this is 13 halves of a mole. I mean, you could say it's 6.5, but this makes it a lot more obvious that we're canceling out the 2's in here. Of course, we don't want to leave that in there for now. Later in the semester, when we study what are called thermochemical equations, we will have these kinds of fractional coefficients, but not right now. So let's clear it out and let's multiply everything times 2 so we can multiply out that half fraction there. So now I end up with 2C4H10 plus 13O2, giving me 2 times 4, it's 8 CO2 plus 2 times 5, 10 H2O. Let me zoom in a little bit here. Thank you. There we go. And now it's a matter of putting in the physical states. Butane. I told you what butane is, right? Lighter fluid. So most likely this is going to be liquid. Of course, we know that in its natural form, without any other information, we're going to say that oxygen is going to be a gas. So is CO2. And water, they didn't tell us, but let's assume that because we don't see water dripping out of our cigarette lighter or whatever it is that we use butane for, we can leave this assuming that it's going to be vaporized into a gas form. Oh, there you go. So this is a trick we can play. And of course, for the moment, we are going to clear out those fractional coefficients by multiplying out the denominator so we can have whole number coefficients. Later in the semester, we might leave the fractional coefficient in there because we'll be interested in the energy production per mole of our fuel here, our combustible here. As we're going to see in the next section, many of the reactions that we study happen in an aqueous solution. In other words, a mixture with water, and the substances are dissolved in there. So let's try balancing an equation where we have these kinds of compounds and see what do we do with polyatomic ions. Here's the reaction. In an aqueous mixture, aluminum nitrate reacts with potassium sulfide to form potassium nitrate and solid aluminum sulfide. Let's go to our paperboard to balance this equation. Okay, in this particular chemical reaction, we're going to have to deal with polyatomic ions. So the first thing we have to do is make sure we have the formulas right. So we have aluminum nitrate reacts with potassium sulfide to form potassium nitrate and solid aluminum sulfide. All of this in an aqueous mixture. As we'll see in the next section, in an aqueous mixture, these compounds actually are dissociated into their particular ions, with the exception of that product that says solid aluminum sulfide. So let's see what we have here. Since these are going to be ionic compounds, we know that the aluminum is going to be in the form of an ion, so it'll be La3+. And of course, the sulfide ion is going to be S2-. Then we have potassium and we have nitrate. So the potassium, you know what it is. Nitrate, you may have to look it up and find out, well, it's NO3 with a -1 charge. So let's build our compounds. Using the crossover method, we'll find that this is Al. There'll be 3 nitrates, so we need to put parentheses in there and make sure we don't have NO33, but Al, NO3, 3. And then we're going to have potassium sulfide. Again, we do the crossover, and we have K2S. Now let's look at our products. Our products are potassium nitrate, that's a 1-to-1 ratio, KNO3. And then the other component, aluminum sulfide, again, crossover, and we get aluminum 2S3. We'll worry in a moment about the proper physical states, okay? We'll worry about that in a moment. All right, let's go ahead and let's see how these compare. I'm going to draw my little dividing line there. And the important thing here is to consider that in this type of reaction, notice that the polyatomic ions stayed the same. So what we're going to do here is we're going to propose that polyatomic ions, I'm sorry, let me zoom in a little bit in there, act as one. So rather than try to balance each nitrogen and each oxygen, I'm going to balance the whole polyatomic nitrate ion. So when I write down my species here, I'm going to say that I have Al, and there's one of them, NO3, and actually this is Al, but we can write the charges if you want, and there's 3 of these. We have potassium ions, and there's 2 of them, and then there's sulfite ions, and there's 1 of them. See, I kept the nitrate as a single entity here. Let's see on the other side. We have now aluminum at 2. We have the NO3 ion. Right now we have 1. We have potassium ions at 1. And we have sulfite ions at 3. So now it's a matter of choice. Notice that on both sides of the equation, each element is present in only one of the components. So I can start wherever I want. So I'm going to go alphabetical. Let me start out by balancing the aluminum. How about that? So I have 1 here and 2 there. So a single coefficient of 2 here is going to change my aluminum here into 2, and that'll work. But notice that in doing that, I also changed the nitrates to 2 times 3, so I change it to 6, and that was as a consequence of step number 1. So what I can do now is I can come back over here on this side and say, well, I can either come on this side now and try to balance the nitrates. Let's try that. So I need 6 of them, which means that this won't work here. So let's go ahead and make this 6 here as step number 2. And so this will become now 6 nitrates. But as a consequence of that step, I'm also changing the potassium. So I'm going to use a downward slash here, right? Because also as a consequence of step number 2, I changed the potassium to 6. So now I have 6 potassiums here and then 2 over here. So easy to fix. I'm going to put a 3 over here. This will be step number 3. And as a consequence of step number 3, I now have 6 potassiums here on the left side. But notice that also as a consequence of that step, and again I use a downward slash for things that were not directly caused by my intervention, I now have 3 sulfites here on the left side. But guess what? That's exactly what I needed. And this is typical. Usually after 2 or 3 steps, if there is one remaining element, it typically gets balanced out. So let's go ahead and rewrite it now with the proper physical states. It says that this is all in an aqueous mixture. So what that means was that when I started, this aluminum nitrate compound was in the form of an aqueous solution. That's the symbol AQ. And so was the potassium sulfide. And now my products are 6KNO3. There's no more information to tell us, so we assume that that is still in solution. However, it tells us there's a solid aluminum sulfide, which means that our last compound here, Al2S3, is actually now a solid. And this is an example by looking at that last component there. Notice that we started with a perfectly clear, transparent mixture. We call this a homogeneous solution, a homogeneous mixture, homogeneous mixture. And now we have a heterogeneous mixture because we have a solid being formed. This is what is called a precipitation reaction. And we will study these in the next chapter, in the next section of this unit. Thank you. Okay, students, now you have some different scenarios, some practice problems. Now please go to your end of the chapter problems and be careful that you look for the correct chapter depending on which edition of the TRO book you have. Some of you may find these exercises at the end of chapter 3, some of you at the end of chapter 4. And when we come back, we're going to focus then on chemical reactions that happen in an aqueous environment. I'll see you soon.